A decay chain is one of the clearest examples of nature changing one thing into another in a precise sequence. In nuclear science, it describes what happens when an unstable atomic nucleus releases radiation and becomes a different isotope. But many radioactive atoms do not make a single jump straight to stability. Instead, they pass through a whole series of intermediate forms. One nucleus decays into a daughter isotope. That daughter may still be unstable, so it decays again. The process continues until the chain finally reaches a stable isotope whose nucleus no longer has excess energy to release. A useful way to picture it is not as one explosion, but as a controlled line of falling dominoes, where each step creates the conditions for the next. The reason decay chains exist is that some nuclei are not balanced. Atomic nuclei are held together by powerful forces, but those forces only produce long-term stability in certain combinations of protons and neutrons. If a nucleus has too much energy, too many neutrons, too many protons, or an arrangement that is otherwise unstable, it can transform by emitting radiation. That emission might change the number of protons, the number of neutrons, or the energy state of the nucleus. Because the identity of an element is defined by its number of protons, radioactive decay can actually turn one element into another. This is called transmutation, and decay chains are the repeated transmutations of unstable nuclei over time. The terms parent and daughter help describe each step in the chain. A parent isotope is the radioactive isotope that decays. The product of that decay is called the daughter isotope. If the daughter also decays, its product can informally be called a granddaughter isotope. These labels are not about age or biology, they are simply a way to track ancestry through nuclear transformations. For example, uranium can decay into thorium. Thorium can then decay into radium. Radium may continue onward through several additional transformations. At each step, the nucleus has changed in a measurable way, and the new isotope has its own nuclear properties, including its own kind of radiation and its own rate of decay. A concrete example helps make the idea less abstract. Uranium-236 contains 92 protons and 144 neutrons. When it decays, it can produce thorium-232, which has 90 protons and 142 neutrons. That means the nucleus has lost 2 protons and 2 neutrons, changing not only its mass but also its elemental identity. Thorium-232 is not the end of the story, because it too is radioactive. It can decay into radium-228, and radium-228 continues the sequence through more radioactive products. After multiple decays and transmutations, the chain eventually ends at lead-208. Lead-208 is stable, so the nuclear domino effect stops there. The endpoint of a decay chain is important because it marks the arrival at nuclear stability. A stable isotope is not completely motionless inside, but it no longer has the surplus nuclear energy or imbalance needed to produce another radioactive emission. Scientists often describe this as reaching a ground state. The nucleus has settled into an energetically stable arrangement. The chain ends not because time runs out, but because the final isotope no longer has a reason, in nuclear terms, to keep changing. In the uranium example, lead-208 acts as that endpoint. It is the final resting place after a long series of unstable forms have transformed step by step. One of the strangest parts of radioactive decay is that the exact moment when a single atom decays cannot be predicted. If you watch one unstable nucleus, there is no known hidden clock that tells you when it will transform. It may decay almost immediately, or it may last far longer than expected. The process is fundamentally random at the level of the individual nucleus. But when scientists observe huge numbers of atoms, order appears. A large population of identical radioactive atoms decays according to a reliable statistical pattern. So decay chains combine two ideas that feel contradictory. Each individual event is random, while the overall behavior of a large sample is mathematically predictable. That statistical predictability is described by exponential decay. For a particular isotope, scientists define a decay constant, usually written as lambda. This number describes the probability rate at which atoms in a sample will decay. If you begin with a population of unstable atoms, the amount remaining over time follows a smooth exponential curve. Early on, many atoms are still present, so many decays occur. Later, fewer radioactive atoms remain, so fewer decays occur in the same amount of time. The curve never depends on how old an individual atom feels, because atoms do not age toward decay in the ordinary sense. The probability remains tied to the isotope itself. Half-life is the most familiar way to express this behavior. A half-life is the time required for half of a given number of radioactive atoms to decay. If a sample starts with 1 million atoms of a radioactive isotope, then after one half-life about 500,000 remain. After another half-life, about 250,000 remain. The amount keeps being halved, not reduced by the same fixed number each time. This is why radioactive decay can become weaker and weaker without instantly reaching zero. The half-life is directly connected to the decay constant. A larger decay constant means faster decay and a shorter half-life, while a smaller decay constant means slower decay and a longer half-life. Half-lives vary across an astonishing range. Some radioactive isotopes decay almost immediately. Hydrogen-5, for example, exists for less time than it takes light to cross the diameter of its nucleus. Other isotopes persist on timescales that are almost impossible to imagine. Tellurium-128 has a half-life of about 2.2 times 10 to the 24 years, vastly longer than the current age of the universe. This enormous range means that not all radioactive materials behave alike. Some produce intense bursts of activity over a short time. Others change so slowly that their decay is only detectable through careful measurement. A decay chain can include both faster and slower steps, making the overall behavior more complex than a single half-life. Because a decay chain contains several isotopes, scientists need more than one half-life to understand it. Each member of the chain has its own decay rate, and the amount of each isotope changes over time. A mathematical framework called the Bateman equation predicts the relative quantities of all the isotopes in a decay chain as the process unfolds. It helps answer questions like how much parent material remains, how much daughter product has accumulated, and when later products become significant. This matters in nuclear science, geology, medicine, and radiation safety, because the danger or usefulness of a sample may depend not only on the original isotope, but also on the radioactive daughters it creates. Over very long periods, some decay chains can approach equilibrium. In this context, equilibrium does not mean nothing is happening. It means the production and decay of daughter isotopes have settled into a stable relationship. The parent continues to decay, daughters are produced, and those daughters also decay, but their relative amounts follow a predictable balance. Reaching this condition can take an extremely long time, even billions of years, depending on the half-lives involved. A sample in equilibrium produces radioactivity in a steadier pattern, slowly decreasing as the original material is ultimately consumed. Understanding equilibrium is essential because the radiation from a sample can come from multiple isotopes at once, not just the starting material. The most unintuitive part is that a radioactive sample can sometimes become more active before it becomes less active. This happens when the material is out of equilibrium, such as when a radioisotope has been enriched or depleted compared with what the natural decay chain would produce. If daughter products are more radioactive than the parent, their buildup can temporarily increase the total radioactivity of the sample. In other words, decay does not always look like a simple downward slide at every moment. The chain matters. The parent, daughters, half-lives, and equilibrium state all combine to determine what radiation is actually produced. A decay chain is therefore not just a list of isotopes. It is a dynamic nuclear story, unfolding through probability, time, and transformation. If you found this helpful, please like this video and subscribe for more explainers.